So there are four different techniques to immobilize an enzyme. One is adsorption, another one is covalent bonding, another one is entrapment or encapsulation, and another one is cross-linking. So let's go one by one. Yeah? So adsorption technique. So adsorption technique is a surface phenomena. So surface phenomena, which means there will be no chemical reaction. Whatever we are going to do are completely physical process. So what we are going to do is like you take a solution, you add enzyme, and then you dissolve them. So enzymes will be in dissolved state, and then you weigh some porous material, say for example silica, silica, and then you add them inside the solution. So imagine these are your silica particles. So what will happen is like your enzyme will get attached to those silica particles. Yeah. So eventually they get adsorbed. So if you have higher surface area, imagine you have a material with a really big surface area, so you will attach more enzymes because you have more surfaces, which means you can attach more enzymes onto those extra surface or additional surface area. Yeah. So that's the principle of adsorption. And normally they select some material with really has high surface area. It can range from 500 meter squares per gram to 1500 meter squares per gram. Although we have material that can exceed these numbers, in most of the commercially available materials are typically they have a surface area in the range of 500 to 1500 meter squares per gram. Yeah, so this is almost like a quarter the size of football field. So every gram will contain enormous quantity of surface area, which means you can load really a large amount of enzyme onto those materials. So that's the principle of adsorption. And also it's like so why if you, so why the enzyme need to come and stick onto those surfaces, and that happens due to physical forces. It can be due to van der Waals interactions, or sometimes it can be due to electrostatics for enzyme or molecules, like if they contain some negatively charged atoms, and if your surface contains some positively charged atoms, they can attract towards each other, and that way your enzyme can stick to the surface of your material. And normally this solid material is called adsorbent, and your enzyme is called as adsorbate. So if you think about this is purely physical process. Yeah, it's like there is no chemical reaction. So something from your solution is go- is getting adsorbed onto a solid particle. Yeah, or surface of the solid. So there is no big bond breakage, or there is no bond formation. Yeah? And that's why sometimes it which means so whatever you is getting attracted onto the surface, they are due to some very weak forces. Typically, if you calculate the energy of adsorption, it will be roughly around 20 kilojoules per mole. This is really low quantity. Imagine if you are doing some adsorption experiment and you already adsorbed your enzyme onto the solid surface. Even if you increase the temperature slightly, say by 10 degrees centigrade, then this enzyme will come back to the solution. We call it this phenomena as desorption. Yeah? So these type of materials are highly vulnerable to temperature or even pH. Just imagine if your surface attracts your enzymes and they are bound by some electrostatics, and if you change some pH in the solution, that's more than enough to pull back your enzyme from the carrier particle or your adsorbent back to the solution. So that's why many industries they don't like this technique in particular, because it's like they have to pay always attention to the temperature, and normally during a biological reaction you can expect some mild fluctuation in the temperature, and that's more than enough to change the property of the immobilized enzyme. Yeah, so you can your enzyme might be dissolved and come back to solution, and it's going to affect your product quality. So this is not a these are some limitation of this technique. Yeah. but this project, this how do you call, like, this technique have some really good advantages. So one is like, anybody can do this experiment. If I give you an enzyme, you can go to a lab, just to dissolve your enzyme, take the adsorbent, put it inside the, even using a simple conical flask, add your enzyme, and then you agitate for some time, and then you can make your immobilized enzyme, which means manufacturing this uh, immobilized enzyme using adsorption technique is really simple. And another thing is, like, if you are really good chemist, you can make this solid material with some functionalities. Yes, say some hydroxyl group or carboxylic group, so that they can specifically attract your enzymes. So if you want, you can tailor the surface functionalities of your carrier particles, so that they can specifically attract some enzymes from the solution. So these are some advantages. Yeah? But in industries, they don't prefer this technique in particular. So that's the thing you have to remember about adsorption. Think I covered all this topic. Yes, the another one is enzyme immobilization in a polymer matrix, or we call it as a microcapsules, like entrapment technique. So what we do here is, like, we trap or we encapsulate an enzyme within a polymeric matrix. And normally this polymeric matrix have like enormous quantities of interconnected pores. Yeah, so just imagine you have some large polymer matrix with completely interconnected polymer matrix, and you also have some pores, and you will entrap the enzymes within those channels. Normally we call those pores as those channels as pores, and some it can range from few nanometers, say from 1 nanometer to even to 50 nanometer. So depending on the type of material that you are using, so you can entrap those enzymes within those channels, or if you want, you can call them as pores. Or some cases, or in they also entrap, they will take a membrane, and then they will entrap your enzymes inside those membranes. So your substrate can penetrate through those membrane, so that it can reach to the active site in your enzyme. And then once your enzyme converts your substrate into products, the product can also penetrate back from the through the membrane back into the solution. Yeah? So these two are like a slightly different technique from adsorption, and and both of these techniques allows to immobilize your enzymes. and and the advantage is like it's very easy to synthesize a polymeric compound, and it's even more easy to put enzyme into that polymeric matrix. There are so many techniques available, and every day there is one scientific article getting published in this area. So if you go to open literature, there are numerous techniques developed by so many scientists around the globe, yeah, including few researchers from our own university. So so this is such a simple technique. If you have a bit knowledge of polymer chemistry, and if you know how to make the right type of polymeric material with a good level of porosity where you can encapsulate your enzymes, then this is really a very good technique. But but this technique suffers by some key some practical issues, which are in fact those are really engineering problems. Yeah. So one is the mass transfer limitation. I already discussed about what is mass transfer. Like it's driven by some concentration gradient. So your molecules will move from high concentration zone to low concentration zone. High concentration via diffusion. So imagine if you have a polymeric matrix, yeah, and just imagine these are your pores and these are your enzymes loaded into those pores. Then if you have, imagine everything is inside your reactor, and if this is your substrate needs to, substrate is at high concentration in the solution, and there is nothing inside the pores. So naturally by diffusion it's going to diffuse through these pores, and then eventually it comes to the active site of this enzyme. And once the enzyme convert your substrate into product, again your product have to diffuse back, because you have less concentration of product in the solution, but you have high concentration of product inside the pores. So by diffusion it's going to come out through the pores, and then it's going to come out into the solution until there is an equilibrium between your substrate concentration in the solution and inside the pores, and also your product concentration within the pores and from in the solution. Yeah. So that's how it's going to work. So you have some diffusion limitations, so you have to take care of these issues. And sometimes like your pores may be so small, and if your substrate molecules are really large, say if your pores are small and your substrate are large, it cannot penetrate through those pores. So if your enzymes are inside those pores, which means they will be inaccessible to the substrate molecules. Yeah. So which means your substrate can never reach those enzymes which is already loaded into that polymeric matrix. So you will have some steric hindrance at the entrance of your pore. Yeah. So this is another problem. And another issue is like imagine you have this solid matrix, polymeric matrix, and you have some enzyme. So enzymes are highly concentrated here, and you start your experiment with zero concentration of enzyme in your solution. So there is a chance that enzyme can diffuse back from your pore to the solution. They call it as enzyme leakage. So this is another issue by where you encounter when you are going to immobilize your enzyme using a polymeric matrix, or when you load your enzyme into some microcapsules. So diffusion can affect the efficiency of the process in more than one ways, more than one. So like a different mechanism, like one is your steric hindrance, and another one is like your enzyme leakage, and another issue is like you need you need to take care of the mass transfer limitations. Yeah. So these are few issues that you should consider when you are going to immobilize enzyme using a polymeric matrix. Need to check the notes. What is missing? I think covalent bonding. So as the name indicates, so what we are going to make is like we are going to use a technique that rely on the formation of a covalent bonding. Yeah, like what we do is like you have some substrate, or if you want to, sorry, you can call it as a solid matrix. I don't want to confuse with substrate. Substrate is your chemical which you want to convert them into product. Some people they also, when we talk about just about enzyme immobilization, some people they call these carrier particles as substrate. Yeah? So just assume this is your carrier particle, and this carrier particle contains some lot of functional groups. So they can form a covalent bond with the amino group in your enzyme, or maybe carboxylic group in your enzyme, or maybe phenolic group, and then sulfhydryl, and also imidazole, indole, even simple hydroxyl group. So they tend to form covalent bond with any of these group in your enzyme. So thereby it will get stick to the surface of your solid matrix. And mostly these substrate particles, it will form this covalent bond only with some part of your enzymes. So and and other than that it will not react. They remain chemically inert to the enzyme, so it won't react with enzyme, so that the properties of your enzymes will not be altered. Yeah, but but still there are this this technique suffer by few limitations. Is like sometimes it can chemically modify your enzyme, and it can make your enzyme to lose your shape. Just imagine, once it formed your covalent bond with your substrate, it can change that shape of your enzyme, which means we call this as enzyme denaturation. So in this process, it will also lose its active site. So which means your substrate cannot enter to those active site, or if you want, you can call it as active spot. So this is one of the main advantage of this technique. And this technique also suffer by another issue. Like I said to you in adsorption, if you have a high surface, you can load more enzymes. But for this type of technique, the based on experience by several researchers, what they found is like the enzyme loading is very low. Like if you have 1 gram of your carrier particle, all you can load is not more than like 0.02 gram of enzymes. So this is not a great technique, yeah, because your enzyme loading is really low. Imagine, even if you take a packet bed, and then if you load these particles, even if you load say like a 4 gram of your carrier particle that contains enzymes, so each gram will contains only 0.02, which means your enzyme concentration will be 0.2 multiplied by 4 is only 0.8 gram of your enzyme. Yeah? Even if you load your packed bed with 4 gram of your, even if you pack your bed with 4 gram of your particles loaded with enzymes, it still you contain very less concentration of enzyme within that bed. So this is not a good idea, especially if you want to convert a large quantity of your substrate to products. And also this technique is remarkably complex. Yeah, like even if you read a book, or you read a procedure from a research article, and if you want to repeat it in the lab, it's not an easy task to do. It's highly complex, and you need very high level of chemistry knowledge. Yeah, if not, you will denature your enzyme, and which means these enzymes will not do the job, which is to which is to associate with your substrate and convert them into products. Yeah? So there are several limitations, in fact huge limitations to these techniques, and that's why industries they don't prefer this technique. even even in labs many scientists they don't prefer to use this technique, covalent binding. Yeah? It's too much chemistry, that's another reason. And even if you are a good chemist, at the end of the day it can denature your proteins, yeah, due to the chemical bonds involved. So this is something you should remember. I might ask some questions in the exam, like to give some general opinion about what type of enzyme immobilization technique you will go for. If these are the problems, or I want to convert something like large quantities of my substrate into product. So tell me what are the enzyme immobilization techniques will be good. Yeah. So you might expect some open-end questions in the final exam. Let me check my notes one time. Yes, and few more things I forgot to mention. When you talk about the covalent bonding, some some researchers they use they they use the cell debris. Imagine they break the cell to take the enzyme out, and this is going to leave some cell debris. They try to connect these cell debris using some interlinking agent. Yeah, so they are, maybe you can call like cross-linking agent. So what they do is like you have a cell debris and then you have an enzyme. So they cross link your enzyme with those cell debris. So that's one way via covalent bonding. So this is something you should remember. Yeah, and many other cases they just use cellulose. Cellulose to where they will load your enzyme via covalent bonding. And finally, I'm going to cover enzyme cross-linking. I think I covered everything. Yeah, cross-linking is like this is again this is a hardcore chemistry, so lots of chemistry. So in this one, instead of carrier particles, like no carrier particles, what they do is like you have enzyme. These are enzyme, and then they use some cross-linking agent to connect all these enzymes. So there won't be additional solid particles like a polymer or a silica based material. They just cross link those freestanding enzymes using some external agent to cross-link all those individual enzymes, so they so that they will remain intact. Yeah? And normally, since it involves some covalent bond, so after cross-linking, the enzymes are vulnerable to lose its shape. Yeah, so this is one key limitation or main disadvantage of this technique. So it can modify the properties of the enzyme, so thereby it can decrease the enzyme activity. So one enzyme may be good, another enzyme it might lose its property due to this cross-linking effect. So ultimately it's going to decrease the enzyme activity. And the key advantage is like you your enzymes are freely standing in the solution without any support, and that's good because you don't have this mass transfer limitations. Your substrate can go and directly sit on the enzyme packets. Yeah, so there is no mass transfer limitation. So that's one key advantage of this cross-linking technique. and many industries like this technique for this particular reason. So there is no mass stands for reason, and also it's like it's very simple methods to produce. Once you have an enzyme, if you know the cross-linking agent which one to use, then you can produce this in no time. So and also since the enzymes are connected via covalent bond, there is no leakage of enzymes as in like encapsulation technique or in adsorption technique. So you won't have any enzyme leakage. So these are some advantages of the cross-linking techniques. I think with this I'm going to stop recording this lecture. I think I covered this enzyme immobilization. I'm going to upload the notes as well because to cover this topic I used some research articles. So I'm going to upload the original article and also the PowerPoint for this particular topic, enzyme immobilization. And in this next lecture I'm going to cover downstream processing. Like I'm going to give only an overview for this module. That's more than enough. Maybe in the CG4017 we will study in detailed each downstream unit operations, like how to design them, how to perform some calculations. For this module all we are going to learn is some theory, and after that I'm going to finish this module and I will try to solve a few problems in mass balance, and I will try to solve a few problems related to enzyme kinetics in this week and also in the next week, and then you can start preparing for your exams. Thank you.